This is Vamshi Vijay Nakkirtha, one of the senior software manager at AWS. Today I'll be talking about evolution of OpenSearch vector database and its path to trillion-scale vector workloads. Before jumping into the journey, I'll walk you through the basics of vector search, the role of OpenSearch Vector DB, and then take you through the journey. We have multiple phases of workloads, so I'll talk through the use cases, how OpenSearch was able to tackle these use cases, and then the roadmap for the next few quarters, and any questions after that. So let's dive into the basics. So what is a vector? So think of vector as a numerical representation of your data. Your data could be a text, image, audio, video. So when you pass this data through the embedding models, it generates vectors. And these vectors capture the semantic meaning and the content relationships. And the dimensions of the vectors can range from tens to thousands. It depends on the embedding model you use. And these vectors are more of like an array of floating point numbers. So each dimension represents 4 bytes of numerical data. Then what is vector similarity search? So we have seen that the models are able to take these data formats, different data formats, and able to generate vectors. So think of these vectors as points in a high-dimensional space. Now, you could say the two vectors are similar when they have similar meaning and context. The position and the orientation of these points in the space determine the relationship between the objects. So to understand whether 2 points are closer, 2 points are similar, you need a way to measure the similarity. So there are multiple ways to do it. The popular ones are Euclidean, cosine, dot product. In Euclidean, the distance determines the similarity. The shorter the distance, the closer they are. In cosine, the angle determines the similarity. The smaller the angle, the better they are. The dot product, it's similar to Euclidean. The magnitude and the direction determines the similarity. Think of a simple use case. So let's say I want to build a recommendation system for my music albums. Consider I have a library of these albums, and there are millions of these albums, and I want to provide a recommendation system. So one simple way to do is take these millions of albums and pass it through an embedding model. It would generate these million vectors. Now, using a library, you could plot this, you could build an index out of this. And then when you are now given a query album, so you are listening to an album, and now you want to find the similar albums. So the idea is take this album, pass it to the embedding model, it generates the query vector, and now the goal is to find the k nearest neighbors to the query vector. So the philosophy is very simple. Give your different data formats, be it text, audio, video. The embedding models converts into points, and then given a query vector, the goal is to find the k nearest neighbors to the query vector using Euclidean, cosine, or dot product. Now, what role does OpenSearch as a vector database play in this? So OpenSearch as a vector database has an ability to build, store, scale, manage, and search vectors at a low latency and optimized cost. So all these millions of vectors that are generated by these models need to be persisted and scaled. So OpenSearch does it for you. And the best part of OpenSearch Vector DB is, alongside providing a vector search, it also has a rich search engine capabilities in terms of filtering, aggregations, and it has observability, analytics, which all help you to simplify and accelerate enterprise application development and make your enterprise search smarter. So let's zoom into the vector database, right? So what is an OpenSearch vector database behind the scenes? It's an OpenSearch cluster. You have data nodes, and you have cluster manager nodes, and you start by indexing your data into a vector search index. So you would send your vectors as JSON to an index. An index would be composed of multiple shards, and these shards are distributed to data nodes. Now, as you index your vectors, they go and sit into the data node, and on the data node, the vectors are indexed using different algorithms, which I'll walk through in the next few slides. And during search, the query vector lands on the coordinator. The data node which receives the request becomes a coordinator. The coordinator has a view of understanding which all data nodes has these shards. So it is responsible for routing the request to all the data nodes containing these shards. And then once the data node receives the request, it runs the k-nearest neighbor search and sends the results back to the coordinator. The coordinator reaggregates all the results. It finds out the top k neighbors among all of those all of the neighbors written by the shards, and then sends it back to the user. Let's take a look at the vector index. So a vector index is just like any other OpenSearch index. You need to define the setting index.knn true, which lets the OpenSearch to enable the vector search codec. So codec is a way of reading and writing the vectors. So it's a Lucene terminology. And then you could define your mapping. So you could define your field where you want to store these vectors. You can mention the type. The type is knn vector. You could mention the dimensions, and then you can mention the space type, Euclidean, cosine, or inner product. Okay. So let's zoom into the shard. So as the data flows into the OpenSearch cluster to the data node, it sits inside the shard. So how does it is made available for search, right? So as OpenSearch has the concept of refresh interval. So during the refresh interval or during the merges or flushes, it takes all the vectors in the memory and then constructs a graph and serializes and puts it along with the Lucene segment files. So Lucene segments has multiple files for different use cases, for prefix searches, regular expression searches. Similarly, now we introduce a new file format that can store the graph data structure or the centroid-based data structure. And during search, the request lands on these shards. It goes through each and every segment. Now, within every segment, it tries to run the k-nearest neighbor search, retrieves the k neighbors out of the segments, aggregates them, and sends it back to the coordinator. So with these basics, now let's get into the evolution of OpenSearch and its path to trillion-scale vector database. So the inception of OpenSearch Vector DB happened in 2019. It's way before the GenAI boom. The innovations in embedding models has unlocked more and more use cases, leading to unprecedented increase in the search of vector workloads over the past 5 to 6 years. Like the popularity of embedding models, generating vectors for images, then audio, video, text, multimodal, generative AI applications, agentic AI. So all of these started introducing more and more workloads, and that has driven the vector databases to handle such scale. Through next few slides, I would walk through the journey on use cases that driven the workload in each phase, and how OpenSearch Vector DB sustained scaling challenges and built features that unlocked these use cases to let OpenSearch emerge as one of the best open source vector database in the industry. So the inception of OpenSearch Vector DB happened in 2019, between 2019 and 2020. The primary use case that led to the birth of Vector DB is the image and the video retrieval system, primarily driven by the computer vision applications. Vector search was used for finding the similar images, facial recognition, and video scene matching. And then as the embedding models evolved to generate vectors for audio, video, the recommendation systems also evolved. So the vector search was used for product recommendations, movie recommendations, music recommendations. So all these vector workloads led to the scale of tens of millions to hundreds of million vectors. And what is the challenge at this phase? So when we started building this vector database, the naive solution is to run a brute force search. So brute force search can work well when the number of documents are few hundreds of thousands to millions. But as the scale becomes tens of hundreds of millions vectors, the brute force search would give you the latency in the order of seconds. If you look at the applications like recommendation systems, you need faster response times. You need a millisecond, like a single digit to double digit millisecond latency. So this doesn't scale. So what are the building blocks that enable OpenSearch to tackle this case? So OpenSearch enabled support for AND search, the approximate nearest neighbor search. And it had two variations of it. One is the graph-based search, which we call hierarchical navigable small worlds. And then the other one is the centroid-based search, which we call inverted files. So let's take a look at this algorithm. So these are the foundational blocks for vector database. Even today, these power the vector search for enterprise workloads. So diving into the graph-based algorithm, HNSW. So the core idea of this algorithm is to build a graph with edges that connect to the nearest neighbors. So algorithm constructs not just one layer, but hierarchy of layers to steer the query vector to the right neighborhood where it can pick up its k neighbors. So during search, it starts from the random node at a topmost layer. It approximately finds the nearest neighbor on that layer. And then using that as an entry point, it moves to the next layer, a layer below it, and then finds a neighbor within this vicinity. And then using that as an entry point, it goes to a layer below it, and so on and so forth recursively until it reaches the bottom layer. Bottom layer is the place where you find all the nodes connected. So once you land on the node in the bottom layer, it does the search to find out all the k neighbors. So the idea here is for the search query to quickly pass through these layers and reach to the point of interest. So this way you are eliminating the unwanted results from the graph. A simple intuition would be something like you're starting on highways on the top layer, then zooming towards the right city, then taking your local roads until you reach the exact house. So this cuts down the latency. This brings the time complexity to logarithmic, which cuts down the latencies from seconds to milliseconds. We also have the centroid-based algorithm, which is part of the FIES library. So it's called IVF. The idea here is to create buckets, and as you index, add the vectors, partition the vectors into the buckets, so that during search, you can find the closest buckets and then narrow down your search within these buckets. So that's how you would be able to narrow down your search space. So to generate these buckets, first you need to figure out the centroids. The way you figure out the centroids is you need a training. You need to run a k-means algorithm. So OpenSearch lets you index raw vectors and then lets you run a train API, which behind the scenes run the k-means and gets you the k-centroids. Each centroid would be associated with a bucket. Now, as the ingestion flows in, as the vectors come in, you compute the distance of every vector to the centroid and try to put in the closest bucket. Now, during search, the search query is also evaluated against these centroids, and it figures out the closest bucket there, and then dives into the bucket, and then does a brute force search and figures out the k neighbors. So again, like how many centroids to visit, how many centroids to generate. These are all the hyperparameters the algorithm provides, which is called nlist and probes, based on the trade-off between your search latencies and accuracy. So you could change these variables. So now we had algorithms that are able to cut down the latencies from seconds to milliseconds, single digit to double digit milliseconds. But these data structures need to be loaded to memory to bring your search latencies to milliseconds. Be it hierarchical navigable, be it the graph-based, centroid-based, you need these vectors, you need these nodes to be present in memory to make it super fast. It was all good till 2020s. Now, beginning of 2020s, the popularity of the semantic search has changed the way enterprise does their search. So enterprises moved from lexical search to semantic search. The main reason is the NLP models like BERT, they started generating the sentence embeddings, which means we are able to understand the context of a sentence through these models. That means we will be able to build applications that can understand users' query intent and figure out the right documents. It essentially makes your queries smarter. So the applications like enterprise search, legal, medical document search, these all evolved, adding the scale to billions. And now that we have embedding models that generates images, audio, video, and text, it also opened up the doors for multimodal search. So the e-commerce applications like, let's say, shopping cart, where you could just take a photo and search the similar products. So those would need a multimodal capabilities. So all these opened up enterprises to leverage all their workloads, be it text or rich data formats like audio, video, to run through the embedding models and generate these vectors. And the scale moved from hundreds of millions to billions. So what is the challenge at this point? So the algorithms we had previously, the algorithms we have, they need to be in memory. Now at billion scale, the memory would become from few GBs to terabytes. And if you consider replicas, the scale becomes even large. So at this point, adding nodes to scale to the memory is going to be a costly affair. So we need a way to cut down the memory footprint. So what are the building blocks OpenSearch introduced to tackle this problem? So the memory is a bottleneck, so we should cut down the footprint. So OpenSearch introduced the compression techniques using the quantization algorithms. So think of quantization algorithms as a way to reduce your large vector space with continuous values to a small vector space with the discrete values. So there are two ways of doing it. One is the scalar quantization, where the number of dimensions remain same, but within the dimension, you change the magnitude. Like for example, with FP16 scalar quantization, your dimension would reduce from 4 bytes to 2 bytes. With byte quantization, your dimension would reduce from 4 bytes to a single byte. So you're able to achieve up to 75% memory footprint reduction with these techniques. And there are other advanced techniques which OpenSearch added. One of it is the PQ, the product quantization. Think of it as a way to project a high-dimensional vector from a high-dimensional space to a low-dimensional space. So you could break your vector into partitions and then encode every partition with a fewer bits. It gives you massive compression, but the main challenge here is to figure out the training data. The training data that you choose should resemble the production data. Only then the accuracies would be acceptable in the production, so which is a challenging problem. So, but if you are a power user, you understand your data, this gives you massive reduction up to 64x memory footprint. And with the quantization, we are able to cut down memory footprint, but to enable the semantic search, to enable the multimodal search, we should let users bring the workloads in a easily onboardable way. So OpenSearch introduced users to plug in their models. So the major building blocks here are, one is the pipelines, and then the ML commons. So OpenSearch introduced ML commons through which you can bring your favorite LLM endpoints, it could be from your Bedrock, your OpenAI. You can bring your endpoint, plug it into the OpenSearch cluster through ML connectors, through ML commons plugin. It would give you a model ID. And then through pipeline, you could attach your pipeline to an index and say, this is my model ID, and this is my text field. And then let the data flow through the index. So behind the scenes, OpenSearch will do the magic for you. So because you need a model to generate text to vector or image to vector, so that's why you need a model ID there. And you also need a field that needs to be fed into this model. So the field determines, the field is the source of input for the model. So through these pipelines and ML connectors, OpenSearch enabled users to plug it in their indexing and then enable semantic search and the multimodal search. So think of it this way. So now you have a pipeline. The pipeline is plugged into an index. You ingest the data, and then you perform the AND search. Now, so customers have a way to onboard to the OpenSearch with these features. But then soon, the community was able to understand that the semantic search alone doesn't work. The semantic search is good at understanding the context. But what if there are some constants like customer ID or account ID? There is no meaning to it. So in that case, the lexical search works better. So we need the best of both worlds, the lexical search as well as semantic search, to get better results. So this led to the introduction of hybrid search within OpenSearch. So the way the hybrid search works is, it takes those query clauses, it takes your lexical query, it takes your vector search query, and then runs it through the shards. So let me take a step back. So traditionally, when you run a query on an OpenSearch cluster, it goes to the shard, executes the query, gets a single score, and then the coordinator aggregates and then sends it back. But with hybrid search, we need to change the way this mechanism works. So we need the independent queries to get back the scores to the coordinator, so coordinator can combine these scores. Like traditionally, you would use a Boolean query. You could put a text query, you could put a vector query, and then ask the Boolean query to combine the scores. The problem is the scales are different. The text scores can be any floating point number. The KNN scores are between 0 and 1. So combining these scores would give a biased results based on whichever has a higher magnitude. So that's where we need a smarter way to combine these scores. And hybrid search introduced a new processor called a normalization processor. So this normalization processor gets in between the query phase and the fetch phase. So once during the query, once you get the results from the shards, the normalization processor would do the normalization and the score combination. Like it could apply normalization techniques like min-max normalization, L2 normalization, and then the score combination techniques like like arithmetic mean, geometric mean, and harmonic mean. So from our results, from our experiments, we understood that by default, the normalization techniques with min-max and arithmetic mean gives you better results. So that's our default, but you can always add these based on your data workloads. You could slice and dice these techniques and understand which gives the better results. And then some of the community gave us feedback that not everybody relies on the scores. Some of the use cases also relies on the position of the document in the ranking. So OpenSearch introduced the reciprocal rank fusion. So again, this is a new processor. So with the reciprocal rank fusion, you'll be able to plug it between the query and fetch phase, and based on the position of these documents, the ranking would be determined and provided back to the user. So with hybrid search, we are able to, at NDCG 10, the accuracy improved up to 8 to 12%. So you can see here, the score ranker processor is one of the processor we introduced that lets you add the reciprocal rank fusion technique. So now we have hybrid search, and we had ability to do semantic search, multimodal search with the use of pipelines and the ML connector. But then what we also realized is the workloads are not just vectors. It also comes with metadata. So the metadata could be something like, it could be a text describing the vector. It could be a geo-coordinate. So this is where what we realized is to be a top-notch vector database, you have to be a top-notch vector search engine as well. Because once you start applying the filters on metadata, then you might need a regular expression search, you might need a prefix search, you might need a geo-based search. So all of these functionalities are generally provided by the search engines, and which OpenSearch is traditionally a search engine, and then evolved into a vector database. So this gives the OpenSearch an advantage to provide you the better accuracy and gives you the rich feature set to filter your data. So there are 3 ways of doing the filters: the pre-filtering, where you first filter and then do a brute force search. But if the filtered documents are in millions and hundreds of millions, it runs into the scalability issue. Then there is a post-filtering, where you filter after doing the vector search. Here the problem is, it's possible that once you apply the filter, you might not get the K results. Maybe the K nearest neighbors are all from the red color fruit, but you're looking for a green color fruit. So you might not end up getting the relevant results. So we need a way where you can solve the filtering at scale, and you're able to give the K results back to the customer, to the users. So OpenSearch introduced efficient filtering. The idea here is to first run the filters with the Lucene query, get the filter IDs, and then use these filter IDs in the graph traversal. So as you traverse the graph, as you pick up the candidates, you would only consider them as a K nearest neighbor if it belongs to those filtered IDs. So this way, you're able to traverse until you get those K neighbors, and you're also able to scale logarithmically, so that avoids the bottleneck. So now we are able to reduce the memory footprint, and we have an ability to onboard customers to semantic search and multimodal search, and we also introduced the hybrid search. And then early 2020s, the boom of generative AI happened, which introduced the rise of retrieval augmented generation, And vector DBs started powering chatbots, knowledge assistants, domain-specific AI applications. So this further led to the scale from tens of billions to hundreds of billions. So at this point, the compression, the 4x compression would still be costly. So you would need more memory. It adds more cost. And then you can add more further compression techniques, but it would be lossy, which means you would lose the accuracy. So what are the building blocks OpenSearch leveraged to tackle this problem? So OpenSearch introduced disk-optimized vector search. So I can walk you through what is disk-optimized vector search. So OpenSearch introduced, and the philosophy is taken from the disk ANN. So what OpenSearch does is it constructs a highly compressed index. It uses binary quantization, constructs a highly compressed index, and puts it into the memory. And the full precision vectors are put on the disk. So the idea is that during search, during your query, you run the search against the compressed vectors. And this search is going to be very fast because the binary vectors uses Hamming distance, and Hamming distance computations are pretty fast. So you could take the vectors out of this, you could get the k neighbors out of these compressed vectors, and then go to disk to get the full precision vectors. And then you can re-rank, you can rescore again with the query vector with all of these full precision vectors, and finally come up with the k neighbors. So the way it works is, so during the indexing, as the vectors flow in, it goes through the quantization framework. The quantization framework samples the data, samples the vectors, and it does mean at a dimensional level, and then it constructs a threshold vector. And now using the threshold vector, it runs through all the vectors indexed in the segment, and then determines whether the dimension has to be 0 or 1. If the value of the dimension is greater than the threshold, it puts 1. It's less than threshold, it puts 0. And then it builds an HNSW graph with these binary vectors. Now, during search, the query vector would also be converted to zeros and ones, and then it is searched against the compressed index, and then you retrieve the document IDs, the IDs that are the closest neighbors in the compressed index. You don't stop it here. So you take those IDs, then you go to the disk and bring the full precision vectors. Now with the query vector, you run a brute force search with each of these full precision vectors, and then rearrange them and give back the results. So with this, even though you're going at a very high compression rate, you're able to preserve the precision by doing the rescoring, and the accuracy, you're able to maintain more than 90% recall. And also at P90, the latencies are around 200 milliseconds. So it was scalable to up to like tens of billions of vector workloads. And we observed that with disk-based vector search, the cost came down to 1/3. And then we also seen that as these applications grew, users has a problem about choosing the K. And if I choose a larger K, you might bring in unwanted results, because you might bring a document which has a less similarity score. If I choose a smaller K, you might miss out on the important results. So this was adding the noisy neighbor problem. And OpenSearch vector database introduced radial search. So with this, you can define your maximum radius. The radius can be your score-based or distance-based. So when you are traversing through the graph, you ensure that you're only looking at the neighbors which satisfy your radius. Everything beyond that is ignored, so that way the noisy neighbors doesn't come into the final result set. So, and now in around 2025's, early 2024's, the agentic AI evolution happened, and vector database are leveraged for used for memory, reasoning, context retrieval, applied in applications like customer support, personal assistance, enterprise automation. So what we realized is vector has quickly become a core AI infrastructure. So we need to ensure our vector databases scale to trillions of workloads. We are able to manage it up to billions, but now we need to scale to the trillions of workloads. So what are the challenges we are facing during this phase? So the building vector indexes at this scale is a resource and time-intensive operation. So as Corey was calling in the keynote session, so building vectors at a billion scale today can take hours to days. So think about trillions. It can take weeks to even months on a traditional CPU nodes. So we need a breakthrough where you could do a massive parallelization and run these indexes faster. So that's where OpenSearch introduced the GPU-based index acceleration to tackle the indexing problem. And then at this scale, the storage also becomes a bottleneck. So you need a way to decouple your storage from the nodes. So OpenSearch introduced searchable snapshots. So searchable snapshots allows you to move your older indexes out of the data nodes to a remote snapshot, and then let you query them on demand from the remote snapshots. It only downloads the blocks that are required to run the search, so it's efficient, and it can run in a low constrained disk. And then we have the derived source and the partial loading, which I'll be covering in the next few slides. So let's talk about the GPU-based index acceleration. So the idea of the GPU-based index acceleration is that to build these vector indexes on CPU, it's CPU intensive. You would see 100% CPU utilization. And today, OpenSearch has a way to parallelize the index build. You can add more threads and do an index construction parallelly. But even then, the time it takes is in the order of days. So we need a GPU fleet here. So the way OpenSearch does is, in 3.0, OpenSearch released a Docker image using that is shipped with the FIs, with the QES library that has the Kaggle algorithm. And you can build a GPU fleet with this Docker image. And on the data nodes, OpenSearch lets you connect to this fleet. So during the segment creation or during the index creation, OpenSearch would push these vectors into a remote store and then let the vector index component know that you have the job to take these vectors and build the graph faster. And then the vector index build component downloads these vectors. It runs through the Kaggle algorithm using GPUs, and then builds this graph, and then converts it back to the HNSW graph. Because the CPUs only understand the HNSW graph, Kaggle algorithm can be run only on the GPU nodes, so it's important to convert it back to the HNSW. So the beauty of this process is the Kaggle algorithm is compatible to HNSW algorithm. So the way this conversion happens, so you can attend the next talk. One of my co-maintainer, Navneet, is going to talk about the conversion process and how we optimize there. And then once you build the graph, it gives a callback to the data node that, hey, now you have the graph ready, and you can keep it, you can persist it with the segment and make it available for search. So with this, we are able to decouple the index build out of the OpenSearch cluster. So now you're able to just push your massive indexing vectors outside the cluster to the GPU nodes and let it build it in a faster manner and push it back to the data nodes. So now at this trillion scale, we are able to tackle the indexing problem. We also need to make our search faster. So OpenSearch continuously invests in the SIMD enhancements in vector search, for vector search. So as we know, like there are multiple CPU architectures, Intel-based architectures, ARM-based architectures. So we had a good collaboration with Intel team as well in terms of adding this support to OpenSearch libraries. So we recently added, initially we had AVX2, then we upgraded to AVX 512. We recently added AVX 512 Sapphire Rapids SPR, which helps you in boosting the Hamming distance calculation, which further improved the latencies for disk-based vector search. And similarly for ARM, we have introduced Neon optimization, which boosted performance around 15% improvement in latencies. And with SPR, with pop count instruction set, we could see up to 48% higher throughput. So I have added the QR code for these blocks. Please feel free to take the pictures. And it has all the benchmark numbers over there. So now we are able to accelerate index builds. We are able to leverage hardware acceleration for search. But the storage is still a bottleneck. So what we realized is, so once we went deeper into the storage, what we realized is whenever we add vectors, whenever we build indexes, we try to duplicate the vector data in multiple places. So you have the data duplicated in HNSW graph. You have vectors in HNSW graph to power for search. You have vectors in .vec files to power in flat files to power the brute force search, and you have the vectors in the source _source. So in a traditional OpenSearch cluster, whenever you index your data, the source, which is the raw JSON, goes and sits in a stored field, and this forms the massive. This takes a massive storage because it's all strings, and every vector, think of it like 0.12345. Each of the number would be considered as a byte. So in memory, when a vector could take, a dimension could take 4 bytes, on disk it could take multiple bytes. So we did a simple experiment, index 100K vectors, and then we realized that around 60 to 70% of the storage goes to this source. And generally we recommend customers not to use the source in the search response, because in the response all you need is the top K neighbors. The vectors are floating point numbers. It doesn't make sense to the end users. But it is required in the OpenSearch cluster for reindexing, for update by query clause, for update by query cases, and for recovery. In case of node drops, you need a recovery mechanism, so the source is required there. So the idea here was, well, the source is needed for this, but can we piggyback on the vec files where we have the flat vectors already, which we are leveraging for brute force search? And the solution turns out to be yes. We are able to leverage it. So we are able to leverage the vec files to answer your reindexing, disaster recovery, update by query. So with this, we are able to completely cut down the source storage, which reduced the storage footprint by 3x. So a simple, like in the OpenSearch benchmarks, the graph looks very beautiful. So from 219, when you go to 3.0, you would see a 3x drop. So before the storage was 300 GB, it becomes 100 GB. I have sorry, I missed to put the graph. The link, please, you can look at the blog, and it has all the graphs. So this has a massive impact on the storage. Not just storage, what we realized is the force merges also become very fast. Because now you don't have to load this massive chunk into memory. You have lesser data to operate with, so you're able to merge faster. And not just force merges, the tail latencies at P99 have become 90% faster, because now the page caches are not overwhelmed. You have 3x lesser data to worry about. And then the smaller shards, of course, helps you with cluster resiliency and recovery. It helps you to easily move from one node to another node for relocations. So this has helped us to cut down the storage by 3x. So what's next? So far, the GPUs are helping with index acceleration. But then to tackle this trillion vector scale, we need more innovations. Indexing is good, but we still need to optimize the way the OpenSearch nodes communicate with the GPU fleet. So that is, we are investing, we have RFC open there. And then now the next logical step is to introduce GPUs to search. The major problem here is to make GPUs available for search, we have to load these graphs in the GPU memory, and to keep the GPU nodes running with these graphs in memory is going to be a very costly affair. So we need to figure out a price performance mechanism to run this. And the beauty of the way we build the current index build acceleration is it's cloud agnostic and it's hardware agnostic. So today it's GPU, tomorrow it could be an FPGA or it could be some other chip. So we should be able to leverage them for search. And we'll continue to invest, adding the hardware acceleration. As the CPU architecture evolves, the more and more sophisticated instruction sets comes into market. OpenSearch keeps adding them. And then we are also looking into the segment-free vector search. So in some cases, the segments can add overhead. So the idea is to decouple the vectors from the segment and use it in a cheaper store, or use it in a different store where you could build your graphs faster without having to go through the merges. And then smart routing. So today, when the query vector comes in, you go and search all the shards. But technically, you could avoid that. So if you're smartly able to pack only the closest vector in the shards, then during search, you could narrow down to only the subset of the shards. So this way, the throughput can increase up to 3x. We have experiments and we have seen massive results. So please watch out for the RFC there. And then the smart defaults. We all know OpenSearch comes up with various knobs. Again, the idea is because it runs approximate algorithms. Approximate algorithms has hyperparameters. Different users have different trade-offs. Some users need high cost. Some users need low cost, high precision. Some users need low latency, okay with the cost. So these knobs let you manage it. But OpenSearch can be smarter here. So we are investing here to dynamically add these, to tweak these hyperparameters based on your architecture, hardware, based on your traffic. And then the other one is the optimizing discretes. So with disk-based vector search, we are able to cut down the cost to 1/3, but reading from the disk is a costly process. So today, the vectors are spread across the disk. So retrieving those vectors adds latencies. The idea is to put the closest vector together in the disk. So with the disk seek, you can pick up more vectors and avoid more disk seeks, which can reduce the latencies further. And then the other one, sorry, I'm over the time. I'll probably take a couple more minutes. The other important innovation is the Lucene and FIS. So Lucene has been innovating faster over the last couple of years. So Lucene and similarly the FIS. And we have a Lucene engine and FIS engine in vector database. Now we kind of want to merge this. So the Lucene comes up with, Lucene has an advantage to understand all the segments. So it has a global state. So it has some features recently added like early termination, which helps to cut down the latencies by 2x to 3x. It also introduced account filtering. Similarly, FIS is innovating with all the hardware acceleration and with the parallelizing index threads. So we want to use the best of both the worlds. So we are adding we're calling it as memory optimized search. So we are building the indexes with FIS and searching through Lucene. Because both the libraries use the HNSW algorithm, the beauty is you can interoperably switch between these engines. So with FIS, we are able to build faster. Now with Lucene, we are able to get the global view of the segments and leverage early termination and account filtering and all other features. And then we continue to extend to remote stores to make the storage cheaper and also invest in the search relevancy. So we will be adding the multi-tenancy, the RFC is out here. Then the disk-based search phase 2, we will look beyond 32x compression and improving the efficient filters. We want to make this filter smarter and faster, and then add the new innovations like late interaction models and the maximum marginal relevance models. Yeah. So with this, I end my presentation. Any questions? If no questions, thank you.